Assalamualaikum. Good morning, everyone. This is Yuhanis. So, this is the first topic that we are going to continue with for SKO3013. That is alkane, cycloalkane, and alkyl halide. Actually, it's supposed to be quite a long chapter because alkane itself and alkyl halide is a separate entity, and alkyl halide has its own mechanism and its own story. So however, we are going to conclude everything hopefully in one go and see how it will go. But no worries, because this particular topic we are going to do a live session. So you are going to have a chance to talk to me if you have some worry. So begin with alkane. This is something that I think that everybody should know already, because this is back in fundamental days, and from the class that I've conducted with you guys, I can see that this is not a problem. Everybody knows from methane up until decane. So you can revise all of this, and it's true. And physical properties of alkane, of course, we know that the higher number of carbons will give you the higher bonding points. You may see through this that I always relate iso with this particular thing. It looks like a triangle there, or in Malay we call it simpang tiga. So when you see a simpang tiga like that, it is an iso. While neo is a centralized. Okay, so this is common alkyl group. So when previously in class through face-to-face session, I've talked to you when we have substituents such as methane, it will be methyl, and ethane, it will be ethyl, and so on and so forth. However, this particular thing is quite rare, where you have iso group, sec butyl group, tert butyl group. An example of this shall be perhaps something that looks like that. To revise this, please look back into your skeleton or line angle formula, where we have 4 number of carbons and a halogen group. So this is called the common name is called tert butyl chloride. Okay, so its common name, remember it has common name is tert butyl chloride, because the substituent is tert butyl, while the IUPAC name is rather different. Okay, IUPAC, you have to find the longest chain. So perhaps the longest chain is this one. Okay, that is propane. So we will look into longest chain later. And you have at carbon 2 you have methyl as well as chloro. So you have to arrange them according to alphabetical arrangement. So 2 chloro, 2 methyl, propane. So I don't have a good handwriting there, but you know what I mean, right? Okay, so move to the next slide. So this is an example where you have multiple groups. So this is just a methyl or alkyl kind of substituents. Okay, right now we don't have any other groups such as halogens and other functional groups. So we're going to focus particularly on this slide. We only have 3 methyls. So of course 3 we are going to relate them with tri. So if we have 4, you have tetra, and so on and so forth. So if we have tri, then you arrange them as tri methyl decane, because we have 10 carbons. I have shown you this during our recaps. Okay, this is an iso group. See, everything has a triangle. So this is a complex substituent thing, where you have complex alkyl group used by using the longest number chain, and carbon number 1 of the alkyl group is the carbon attached to the main chain. Right? Now, degree of alkyl substitutions. So you may see this example and you will look at this. So this is rather quite complicated substituents, but you may try to figure out by looking at where is the substituent pointed at and what is the number being pointed there. Okay, try to delve into this slide and understand. Now, boiling points of alkane is the same as previously shown you. So melting points of alkanes are actually parallel to the alkane sources. Of course, you may find this in Ketere,
Ketere, Kerte.
Petronas plants. Okay, So these are all where our petrol comes from, and you know the example of alkane. You have seen this actually during your fundamental year. This is just recap. So catalytic cracking and hydrocracking is how you get small chain alkane. This chain, this is just a read through, right? So cycloalkane is something that we have also looked at in the previous in the life class. So you have this type of molecular formula thing, and this is a rather simple and preferred drawings of, for example, cycloheptane with 7 carbons and cyclopropane with 3. This is again a written nomenclature. You have this example of why is it called third butyl, because it's rather simple to call of this as third butyl. Then you want to name it as 1,1, such as like that. This is cycloalkane nomenclature. If there are 2 or more substituents, number the main chain to give all substituents the lowest possible number. You may want to look back at the rule of IUPAC. Okay, rule of IUPAC. A simple Google search will solve this. In fact, I do have it, in one of the slides. Okay, so if you have trimethyl cyclopentane, we are going to number everything 113, because if you number 133, it will give you a cumulative bigger number. Okay, so likewise this example there. Alright, now cycloalkane as substituents. This is a rather more simpler way of naming, because if you want to have your cycloalkane as your parent chain, this cannot be it, because for example this one only have 3 carbons. Alright, while the longest chain here you have 8 carbons. Okay, so of course IUPAC will prefer the longest. This one is reaction with hydrogen, reaction with lithium aluminum hydride, and then reaction, only one reaction, because alkane is very stable. It doesn't have any pi bond, so it doesn't have electrons that can move. Okay, so you may want to click this link, and you will see halogenation reaction example. I don't want really to delve into that because it is a very straightforward reaction. Okay, in this references also you will see the radical mechanism of this halogenation reaction. I think this topic is best discussed live in live session, but I'll try to discuss here as well, so that you have some idea about alkyl halide. So by the name of alkyl halide, literally you have halogen, that's for halide part, and alkyl or alkane, you may say like that, for alkyl part. Okay, so basically alkyl halide is something to do with a halogen atom in the compound. So these are some classes of alkyl halide that you can see. We have alkyl halide, vinyl halide, where we have double bond in the compound, and we have aryl halide with a benzene ring attached to the halogen group. Now with polarity and reactivity, this is something that you may read. And for IUPAC nomenclature, I can see that many of you have some understanding about the name for haloalkane. Okay, basically for alkyl halide, the IUPAC name concerning to it is we will place alkane as our main chain or the parent chain, whereas for the halogen atom it will be the substituent. Okay, so how do we do this? It is the same like we do for naming for alkane, where you find the longest chain firstly. You can see here the longest chain, and then you find where is your halogen located and which carbon. Okay, what halogen, which carbon, and then you place them together, stitch them together. Okay, so over here then you find the longest chain. So the longest chain there is heptane, because hept stands for 7. Okay, so you put hept first, you know it is 7 carbons. Okay, and then you have alkane as the functional group there, as a main functional group there. So you put in, alright, and then you have to find, is there any substituents? Okay, there is a substituent at carbon 5. Okay, so some student asked me, Doctor, is it carbon 5? So you say 1, 2, 3. I think the numbering is a bit wrong here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, so that's why this is supposed to be carbon 4. Okay, so we know at carbon 4 there is a substituent. Okay, now what substituent? Substituent there is actually ethyl. Okay, how do we know it's ethyl? Because Et is for 2 carbons. Okay, so it is ethyl. Okay, so and then, but additionally we also have a fluoro there. Okay, so because of the fluoro there, and you want to number the ethyl 1 and 2, so the fluoro is actually attached to carbon 2. So its full name shall be something like that: 4 dash in the bracket 2 dash fluoroethyl in the bracket heptane. Okay, so this is additional example where it is a longer chain with a nonane 9 carbon. Again, the numbering is a bit wrong here: 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, and the location is like that. And over here is what can you see is actually the observation for alphabets. Okay, where B comes before M. Therefore, even though the number is actually bigger for bromo, it has to be 6 bromo 2 methyl nonane. Observe here as well is that you can see that between between words is doesn't have anything. Okay, but number in between number and words is actually a hash, not a hash, but what do you call this, a simpang, like that, right? It has to be like that. Now with this case, now we are looking at cyclohexane. Literally this one is obviously a cis, because you see that both hydrogen there is actually facing down. Okay, likewise, like we have learned before for RNS, something with instead of with a hash like that is actually facing behind or below. Okay, so we have there is 1 bromo 3 fluorocyclohexane. Okay, now this is a systematic common name. So the alkyl group where it becomes a substituent. Okay, so these are some examples. We have actually looked at this previously in our recap session. Okay, now common names of halide. This is called methylene halide, haloform, carbon tetrahalide. Unfortunately, this is a live session, so I don't have a longer time for me to do some stories about all these halides. But when we gonna face each other again, so I'm sure this will have more stories into this. Okay, definitely have more. Now alkyl halides, these are some clarifications. In live session, okay, this is something that I would like to emphasize, where you may see classifications for alkyl halide and you may parallel them with alcohol as well as amine, because literally how you are going to see them is basically the same. So I always tell my student this is the best way to know about classifications of alkyl halide, alcohol as well as amine. Okay, so how do you see this? So basically you say you have something like that, right? And my X, now X is basically any halogen atom, so this will be chloro, for example. So this will be say I put here R is basically substituents. Okay, let me do an example instead. So I'm going to erase this. Okay, and I'm going to put the real R. R is actually alkyl. Okay, R is alkyl. So say I put here CH3, this is another CH3, CH3, and here is hydrogen. and then this is Cl. Okay, let me erase this so that, okay, hold on. So let me erase this one because I want to show you something. So this will be pen. Okay, CH3, and then this is CH3. But to erase this again, H. Okay, so this one say everything is CH3, you know. So I can change this into an ethyl, for example, and then a Cl. What is basically different in all of this is the number of hydrogen. Okay, with primary halide we have 2 hydrogen atoms. On the concerning carbon, okay, on the concerning carbon, you see at carbon attached to halogen, okay, and then you have 1 hydrogen, 0 hydrogen for tertiary. Okay, so this is the type of dihalides. You may read this in your notes. So these are some examples of alkyl halide. There are many examples of it. Okay, it's very interesting. Dipole moments, of course, with bigger electronegativity. For example, fluorine is higher than iodine. Bond length increase, etc. As well as molecular geometry. Now, boiling points, we know that greater mass will contribute to higher boiling points, and spherical shape will decrease the boiling points. Then density, of course, you may see that alkyl chloride and alkyl chloride are less than the water, and these are some synthesis of alkyl halide. Okay, so it's very important for alkyl halide that you understand its synthesis and reaction, because there are plenty of reaction concerning alkyl halides. So firstly, for example, how are you going to make alkyl halide? The easiest way is through the reaction of alkane. This is something that we have looked at. Okay, now halogenation of alkane. Okay, these are the ways to make alkyl halide from alkane, that you will react them with halogen atom. Okay, halogen, for example, chlorine gas, in addition to H mu, that is the light. Okay, for alkane you have to have this, or else your reaction will not move. Okay, so halogenation of alkene, these are addition of hydrogen halides to alkene. Another way to make alkene is through addition of hydrogen halide. So what it will actually do is, say you have something like that, okay, and then you want to add HCl, you want to add HCl, okay, you want to add HCl, you know, here you only have how many hydrogen? We have 2 hydrogen here, and here we have 1 hydrogen. Now, to add this, you cannot simply add. You cannot simply put, I want to put here and there. No. Okay, it will follow what we call as Markovnikov rule. So, Markovnikov said that hydrogen will be added to carbon with more hydrogen. Okay, while halogen will be added to carbon with less hydrogen. Okay, so for this case, for example, you know this particular carbon have 2 hydrogens. Of course, it's more than 1 hydrogen over there, here. Okay, so because of that, what you will observe is actually 2 hydrogen there. You know, you can, for skeletal structure, you may want to omit the hydrogen. Okay, so you put hydrogen there, because hydrogen, okay, for HCl, you know, HCl is made up of 1 hydrogen and 1 chlorine, so hydrogen will be added there, while here you will add your chlorine. So you want to put hydrogen there, is fine as well. Okay. So this is more examples. Okay, tadi previously we looked into hydrogen halide. Okay, now we have both bromine. So in this case, it doesn't matter where you add because both of them will be the same thing. So allylic is a bit different. You may want to read this, and the best way is kalau bromo you want to use NBS. So what it's actually doing is instead of adding to this particular thing, it will actually add to the carbon next to your double bond. Okay, so in this case of chlorine, the difference is this, the high temperature. Okay, the high temperature. And for bromine, it uses an entirely different reagent. It is called as NBS. Okay, for allylic bromination, you can see that that is something that we'll do. So this reaction mechanism, so the reaction involve are radicals stabilized by resonance. Okay, example of allylic. Okay, you can see that instead of adding to the double bond itself, it now added to the carbon next to the double bond. Now, conversion of alcohol to alkyl halide, as you may see that the topic of organic chemistry is very interrelated. We have actually previously talked about alkane and alkyl halide. Now we are talking about alkyl halide and alkane, alkyl halide and alkene. Now we talk about alcohol and alkyl halide. So another simple way to make alkyl halide is through halogenation of alcohol. Okay, so where one methyl, for example hexanol, there will just replace the OH to the Cl. Okay, another way is using PBr3 or PCl3 if you want, for replacing OH to your halogen that you like. So for example, PBr3 is for you to put bromo there. You want to use PCl3 for putting the chlorine, okay, instead of bromine. So you might want to use SOCl2 as well, thionyl chloride. It will function the same. It's just replacing the OH to the Cl. That's the best way to understand this. So these are the reaction that we have. Two types of reaction actually. It is called as nucleophilic and nucleophilic substitution, elimination. This is where the mechanism of alkyl halide take place. Okay, these are some revision of what we have looked at. These are reaction of alkyl halide. Previously, we have looked at synthesis of alkyl halide. Okay, you might want to do a summary of things. Okay, now I would always like to compare. For substitution reaction, we actually have SN1 and SN2. These are the main comparison. You might concentrate on here. So tertiary alkyl halide will prefer SN1, primary alkyl halide will actually prefer SN2. This is why you need to know what type of class your alkyl halide is. Okay, so but this is substitution. And when we talk about SN1 and SN2, we have steric hindrance and carbocation stability. While and then it says this is something that I found on the internet. It's very, very good. How do I know that it will proceed to either elimination or substitution? And if it is elimination, is it E1 or is it E2? So the best way is for you to look at the type of alkyl halide, and then what sort of mechanism it will involve. Okay, this is SN1 pathway, so tertiary alkyl halide. Okay, then this is where primary alkyl halide SN2 pathway will dominate. Yeah, this is the Site-Zeff rule. So previously I have explained to you Markovnikov rule, where you want to add something. Okay, double bond, add something. Okay, so Markovnikov is from double bond, okay, to a single bond basically, because you are adding something, right? But Site-Zeff or Site-Zeff, okay, depends where you are at, is basically from something, okay, from something. Say you want to have dehydrohalogenation, so you want to eliminate, right? But the end product is a double bond. So here the end product is double bond, here the beginning product is double bond. So basically Site-Zeff said that when you want to make a double bond, you have to make the double bond with the more substituents. Okay, more substituent. I always say like this. Okay, but in this case here, it explained there is for trans and cis. Okay, it's very stereoselective, but I always tell my students that sometimes, you know, for example, you can make something like, you know, this, and you may make something like this from your reaction. So which one is which? Always choose the double bond with more substituents. Okay, like this one, it only have one hydrogen, so this case it only have one hydrogen, right? Over here only. Okay, but in this case it has two hydrogens. Markovnikov prefer this one. Sorry, Zaitsev prefer this one. Okay, for example, you have bromopentane there. Okay, from an alkyl halide, you want to make alkene. Okay, this is a reaction of alkyl halide. So you will observe that this one will be the major one instead of this one, because over here you may see that if I want to draw this, it looks like this: 1 2 3 4 5. 1 2 3 4 5. So it actually looks like that, and this one is actually look like 1 2 3 4 5, and it's actually looking like that. So these are the only hydrogens there. Okay, this one have hydrogens as well as hydrogen there. So this one have 3 hydrogens, this one has 2 hydrogen, therefore we will use this one as a major products. Okay, this is SN2 reaction. You can read this with the mechanism, SN2 energy diagram. I would appreciate that you know, you find your own resources for SN1, SN2, and E1 and E2, or that something that we can also I can discuss with you over the live session. Okay, so these are nucleophilic strength, basicity versus nucleophilicity. Okay, you may read about this as well as the living group ability. Okay, so this is something that I want you to read over. Okay, backside SN1. These are the mechanism, again something that I will explain to you in the live session, inshallah. And this is the structure of carbocation. The trickiest thing about alkyl halide is this part. Okay, the mechanisms. So let me see, between SN1 and SN2 comparison, and that's about it for alkyl halide. Thank you.